Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is yet another video in a series on complex numbers. You should have just watched the video on adding and subtracting complex numbers. Now we go into multiplying complex numbers. Notice that we're not talking about dividing complex numbers because that's a little bit different. But multiplying complex numbers, well, that works just like it would work if they were polynomials. So here's the process, how to multiply complex numbers. Treat them like they're polynomials, because they actually are, and use the distributive property. Always remember that I squared is equal to a -1. That's going to be critical for the mathematics. So let's determine the product of z sub 1 and z sub 2 for the complex numbers in our previous video, and then we'll graph the result as well. So here are the complex numbers from the previous video. You can see it's -2 plus 7/3 I and 1/2 plus 1/2 I. Let me write those down. And now we're asked to go ahead and multiply those two complex numbers together and then graph the result. So multiplying these two together, like I said, is very much like multiplying two binomials together. So multiplying two binomials, you have z sub 1 times z sub 2. That's going to be -2 plus 7/3 I. And let's see, z sub 2 is 1/2 plus 1/2 I. And treat it like it's binomial distribution. Let me use green here. -2 times 1/2 is a -1. And then distributing the -2 over to the 1/2 I, we get a -I. Now I'm going to distribute the 7/3 I to the 1/2. That'll be a 7/6 I. And then finally, last distribution, 7/3 I times a 1/2 I. I'm going to do this kind of slowly. That's 7/6 I squared. But remember, I squared is a -1. So this will become, let's see, we have a -1. The -I plus 7/6 I, well, I is -6/6 I plus 7/6 I is 1/6 I. And then minus, because I squared is a -1, 7/6. And let's see, we can do one last little manipulation here. -1 minus 7/6. Well, -1 is -6/6. -7/6. On top of that would be a -13/6. That is the product of z1 and z2. And again, they want us to graph that, labeling these axes here. So this is the real axis. And then the other axis right here is the imaginary axis. And then what do we want to do? z1 times z2 is -13/6 plus 1/6 I. So I'll go backwards 13/6 in the horizontal direction. That's a little bit beyond -2. So I'll just say that this right here is roughly where -13/6 is. And then up 1/6 in the vertical direction. So that point right there would be z1 times z2. Again, if we consider this to be a -13/6 and this height here to be a 1/6. Now, just as a reinforcement, let's go ahead and determine the product of the two complex numbers from our very first example way back when, and I'll bring those up in a moment here, and then graph the result. And that example was this one right here, where we took the result of a quadratic formula and we rewrote that solution in terms of imaginary numbers and then as complex numbers. So we had these two complex numbers right here. What we want to do is multiply them. These are very special complex numbers. I'm going to go ahead and grab that up. And what we're going to do is when we multiply them, we're going to find out that something very special happens with the mathematics in the background. So let me go over to that page we're just on. We're going to multiply these two together. Now, I want you to pay attention to the form of these complex numbers. They're very close. In fact, their real parts are identical. Their imaginary parts are opposite in sign. And that means that these are called conjugates. And if you've been following my lecture videos so far for a review for college algebra, you should know what a conjugate is. If you don't, we'll define it in a moment. But for now, let's go ahead and multiply z1 against z2 here. So z1, again, I'm going to write as negative 3/2 plus 4i. z2 is negative 3/2 minus 4i. And now doing the distribution process, we are going to take negative 3/2 times the negative 3/2. That will become a positive 9/4. Then we're going to go ahead and take that negative 3/2 and multiply it by a negative 4. That'll be a positive 12/2 I, or in other words, a positive 6i. Now we're going to go ahead and distribute the second term there. The 4i will distribute to the negative 3/2, and that'll be a negative 12/2 I, or a negative 6i. Something very special happens there, obviously, because positive 6i and negative 6i are opposite in sign. They will cancel beautifully, and that will always happen when you're multiplying a number by its conjugate, or a complex number by its conjugate. And let's see, 4i times a negative 4i is a negative 16i squared. Cleaning that up, we know that I squared is a negative 1, and so we get 9/4 plus 16, because again, these two middle terms cancel beautifully. And a negative 16 times a negative 1 is a positive 16. And finally, add those two constants together. 16 is the same thing as 64 over 4. Add 9 to that, that's 73 over 4. Now, I like the fact that I'm asking you to graph the result here. First thing I want to draw before I do that, I want to draw your attention to this. Notice that when you're dealing with complex numbers that are conjugates of each other, in other words, one's a plus bi and the other's a minus bi, when you multiply them together, the result is going to be a real number, no longer a complex number with an imaginary part, but instead, or at least a non-zero imaginary part, but instead a real number, which is a complex number with a zero imaginary part. The other thing I want to draw your attention to is when we go to graph this, I'm just going to quickly scratch out a horizontal and vertical set of axes. When we go to graph this, we're only graphing the real part. So I'm only going to worry about going over 73/4 in the real direction. You don't have to go anywhere in the imaginary direction. That is the point, z1 times z2 on our complex plane. And that gets us to this definition of a complex conjugate. Normally, I would just say a conjugate of a plus b is a minus b, and a conjugate of a minus b is a plus b. When we're talking about complex numbers, the same rule applies. It's just that we call them complex conjugates. I often just call them conjugates. But the complex conjugate of a number a plus or minus bi is defined to be a minus or plus bi. In other words, that central addition or subtraction operation gets flipped. If it was addition, it becomes subtraction. If it was subtraction, it becomes addition. Also, please note the notation we use for conjugates. If z was the original complex number, we call z bar its conjugate. It's just a very nice notation. And in fact, it gets used in a lot of different ways. So for example, 3 plus 2i, if you want to know what the conjugate of 3 plus 2i is, you would write it that way and say it is equal to 3 minus 2i. So that's this notation right here just tells us we're going to look at the conjugate of the complex number that's underneath that upper bar. And as we've said in the previous examples, is that the product of complex conjugates is a real number. The proof is actually pretty easy. Suppose that you're given a number z sub 1. and z sub 1 is just equal to a plus bi. Then the product of z sub 1 with its conjugate, z sub 1 bar, well, that's going to be a plus bi times a plus bi bar, right? That's the conjugate notation. And now we're going to go ahead and insert the conjugate into there. So this is going to equal a plus bi times a minus bi. And now we can do the distribution, which is a polynomial distribution. It's a times a, which is a squared, minus abi plus abi, and then finally minus b squared I squared. And when you clean that up, because the ABIs will cancel, you get this beautiful a squared plus b squared. Again, remember, I squared is a -1, so that's -1 times a negative b squared, so that's a squared plus b squared. And by the way, that is a real number. And that's the proof. That's the proof that the product of complex conjugates is just a real number. So QED, quod erat demonstratum. So it has been proven. As our final example, we're just going to compute some conjugates really quickly. Each of these has a very special result. So for example, z sub 1, if we want to know its conjugate, well, remember, the conjugate is going to be 3. If the original number was 3 plus 0i, the conjugate will be 3 minus 0i, or in other words, just 3. So the conjugate of a real number is the real number itself. Z sub 2 bar, well, that z sub 2 is actually 0 minus 2i, and so its conjugate is going to be 0 plus 2i, or in other words, just positive 2i. So in this case, the conjugate of a pure imaginary number is going to be the opposite of that pure imaginary number. And finally, z sub 3 there, which is 1/2 plus I, its conjugate is actually, I think, for most people the easiest, because it's just 1/2 minus I. So real quick ways to compute conjugates. They end up being incredibly important as you move forward, at least in more advanced math courses. So I don't want you to think that you'll never use complex numbers. You will. It's just that you're going to use them if you go into engineering or computer science, electronics, anything like that, or mathematics.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.